Hi, I'm Ossie Schnorr, Senior Principal Engineer in Computing at GE Research's Forge Lab in upstate New York. The Forge Lab is tasked with looking at technologies that GE businesses feel are important but may not be ready for. Here in the quantum computing space, we have an interactive demonstration which illustrates an application of quantum relevant to GE to get our businesses and our technology colleagues comfortable with quantum. This demo takes the form of an interactive table which allows visitors to craft their own problem and to actually run a D-Wave computer themselves. One example of where quantum would be useful to GE relates to how we service the equipment we sell. Power turbines, jet engines, and medical equipment are highly engineered products that require regular servicing to maintain their safety and peak performance. Our customers see these assets as an integral part of how they make money, and part of our job in sustaining these assets is to reduce the customer's downtime while controlling our costs. An example, asset sustainment, might be the repair shop where there are options on how a repair may be done. Here we see a repair that can be done at the factory on the left or by a technician with the right equipment on the right. But the resources on the floor are shared by many repairs being run in parallel paths. If repair options are not chosen properly, congestion in the work cell of a repair shop can reduce throughput, increase cost, and downtime. To understand the choice of repair path options to reduce shop floor congestion becomes more complex with more repairs. For example, GE has a shop floor where 15,000 repairs share 6,000 work cells. If there are on average 3 repair path options per repair, this results in something like 10 to the 7,000 choices that can be made. Choosing a good one out of that large a number is not easy. To illustrate this complexity, we allow the visitor to create their own shop floor scenario on the table. We then go through and talk about the formulation of that problem for the quantum computer. Our visitors laugh with us when we point out the special nature of this access we are providing them before they push the big button to send a real calculation to the D-Wave machine. After the results are returned, visualizations along with metrics are presented, which the visitor is encouraged to explore. With this information in front of us, we discuss the current limitations of quantum computing in the form of the number of qubits and qubit connectivity. This is where the notion of sampling efficiency and working qubits overhead are pointed out, as well as how these are related to the problem of embedding and the need to do chaining to map logical qubits to working qubits. The question frequently comes up: when can we think of using quantum computing in industrial applications? And for the past 2 years, our answer has been to point out 3 things: when there are more qubits, better connectivity, and a wider selection of hybrid approaches that use quantum computing. This has led us to say that it was a matter of a few years, but our efforts with advantage in the hybrid solutions that D-Wave enables have changed our answer to why wait, or can you afford to wait? Here's what's convinced us. I hope you enjoyed the video. Let's talk about industrial scale. Here's a chart that shows some examples of industrial scale in different application domain spaces. You'll notice that the number of entities that are involved and the number of answers that are involved are quite large. The timescales are also interesting. They mean that you're going to need to do computing more rapidly than you can in classical approaches to get an answer in a timely manner. The value of these is quite large to GE and to our customers. So it's important that we do this and we do it well. So in the past, these type of applications spent a lot of time trying to reduce the order of the problems that they were solving. Or they thought of these as being beyond computational methods to manage, and they would use ad hoc methods like rules of thumb to do them, which works. But in all these cases, there's a continuing effort to gradually improve the outcomes. Most of us aren't involved in quantum to see gradual improvements. We want to see something more grand than that. So I think we have a tough road ahead of us, because if you think about it, there's not a lot of low-hanging fruit here, right? Just the amount of data that is needed to be fed into these operations is quite large. And in the applications that we're talking about here, it's in constant flux, right? So you have to react to the environment in a timely manner. So because of that, these are large systems in general. And these systems either need to be created or you need to integrate in with those systems to bring them together. So even before you can become a quantum hero, you have a lot of work ahead of you. So, for example, in the asset sustainment problem that we demonstrate to our visitors, there's very little likelihood that somebody is sitting on the matrix or even the operations or sets of operations to gather that matrix to even apply it to a quantum computer at all. But there are trends, at least out there, that are helping to improve the outlook for these kind of problems, right? We think about the systems engineering that's going on here, right? The effort by industry to embrace cloud computing is definitely working in our favor. And platform efforts like AWS and Azure are getting to the point now where the data that's going to go into that matrix, it's a good chance that it resides someplace in the cloud and is closed. So things like Bracket, which are bringing quantum computing and cloud computing together, I think are going to have a lot of hope and give me a lot of hope that this is going in the right direction. And it's really nice to see or be able to access a quantum computer with your credit card. I mean, it's truly amazing. Be able to pull out a credit card. If you got an Amazon account, you can access a quantum computer. Pretty darn cool. So, next we really need some machines to do this, right? The machines and the quantum algorithms that can handle that computation. And here there's some good news. So on this chart, we show an example or a screenshot on the left here of the application, the demonstration that we show to our visitors, right? And there's 3 boxes across the top. The first one is looking at sampling efficiency. The middle is looking at the energy, the minimum energy that's reported back. And the one on the right there in the yellow is talking about the working qubit to logical qubit ratio, right? We think about that there. So the first one is really about, hey, how many times you ask the question, do you get back a plausible answer, right? If I ask 5,000 times and I get back 1,000 answers that are plausible and the rest are kind of garbage, that's not so good. I'd like to see a lot more coming back that are plausible, so I can search a very large space more efficiently. Minimum energy is very understandable because I'm trying to find a minima to my optimization or other type of problem. And then the efficiency there is really that working to logical qubit efficiency is really about how big a problem could I put on the machine, right? And so today, the big story for this is around the connectivity, right? That's what we tell our customers. We say, hey, it'll be ready when we have the number of qubits and we've got good connectivity between those qubits. And the Advantage machine is really doing a lot to help there, right? We can see on the right here, these charts, right, where our percentage of constrained answers that come back, those plausible answers, has gone up. And then on the further right there, we see that the number of qubits to get those answers has gone down. So that connectivity has really got a twofold improvement, right? Fewer chains to be broken and fewer qubits being used to be changed, which is a story I'm sure all of you understand. And then it's on the bottom there, it's very comforting to see that the quality of the qubits that are being put into this massive piece of machinery here is still as good as it's ever been, which is a great story. So, we last year at the Qubits in Newport, Rhode Island, which was awesome, we introduced this notion of the perfect embedding, right? We've been working on increasing the size of the problems that we were addressing, trying to get to that industrial scale by applying chaining, chaining-based approaches, right? Start small, build up. Don't worry about connectivity. Just let the mechanisms behind the scenes do the embedding, doing the chaining for us. And we realized that there was definitely a limitation on that approach. So Enrita Gianni and I, GE, we went off and said, what if we had a problem that perfectly fit on the machine where we didn't have any scaling or any chaining issues involved? So we built a very small one, right? One diamond out of the Chimera topography, and said, this is good. And so we wrote some software to scale that up to the entire, to as large a part of the fabric as we possibly could. So we came up with a problem that represented 297 repairs, and they were all two pairs, so two repairs. So that means there's two paths. I can, I got a flat tire. I can either buy a new tire or I can get it repaired, but I don't want to do both, or I don't want to do neither. So I got a two-pair repair. So there are two-pair repairs, which exist in the real world. And then we were restrained on the number of resources that could be shared between those. So right, we're trying to minimize the congestion on these resources. So we could only do two paths contending for one resource. Kind of limiting, but still we got some amazing results in terms of very high sampling efficiency and just the scale of the problem, that right, to the 297 possible answers, and we were sampling out of that space and we were doing it efficiently. We're very excited, and this really got us motivated to be thinking about, hey, maybe we're not that far away from using this to industrial scales, right? So we could almost imagine problems that we could fit into that scaling. And then as part of that, we looked at the advantage. Where was Pegasus going? And we did kind of a back of the envelope calculation on that. And it was, that was kind of interesting to think about. And so this year, what we did is we went and took the challenge of taking advantage and doing this perfect embedding on it as well. So on the right side of this slide, on the left side of this slide, let's talk about that first. Right, we went off and did that embedding. We were able to do on the 2,615 repairs. They're both twopers still, and that's mainly because of our software. But we can now do 3s and 4s as well because of the chaining, or the need to, or the connectivity of the architecture, which is a huge improvement. And we're able to get very high sampling efficiency, which is, again, an awesome thing to understand. And the number of answers that we're exploring now, the spaces, the answers that we're exploring is quite high. So we can imagine a real problem fitting on the Advantage machine just as it is using this approach, right? We can do 2s, 3s, and 4s. And now also the resources, the contention on resources can also be 2s, 3s, and 4s. We can imagine problems being solved by this, which is really pretty amazing. But we still look back at that first chart of the scale of the problems. This is kind of a baby step, it's a great baby step, don't get me wrong, but we still see a limit to the qubit scaling that we're seeing here. And so thanks to D-Wave for giving us access to this, but we got access to their LEAP discrete, I'm going to screw up the name, their DQM solver. And we created a synthetic problem that was in essence equivalent to 44,500 qubits, something that won't fit on a machine for many, many years. But we're able to use this hybrid approach to get an answer. which is phenomenal, amazing. And the answer is so large that it's really hard to tell whether it's right or wrong. So if somebody has a suggestion on how we figure out how good an answer it is, that would be great. We do know that it meets the constraints. We're able to figure that out, but it's a large answer, right? And so if you take a look at that gray bar on the right-hand side of the slide here, that's actually the answer. That's just a series of ones and zeros that represents the answers. So very exciting. And this is really, I think, the kind of moment where it hit us that why are we waiting? This is exciting stuff for us, right? To be able to do this. And we were able to do it in a matter of hours, right? So it's within the time scale of the problems that we put up as examples up there to get these answers. So there is hope here, which is very, very cool. So so I want to talk a little bit about the challenge of this, though, is that, hey, we are talking about a step change here and what we can go after, right? We don't want to necessarily compete with classical computing, or we really don't or can't in many cases. But we still deserve a place in the portfolio of choices that are out there. But so if we go back and we think about, hey, the progression of computing, right, from people writing on clay tablets to people building machines to do computing, to electrical calculators, to digital computers, and now we're talking about quantum computing. If we look back, there's always a chart someplace or a graphic someplace that kind of indicates, hey, this was the turning point. This is the reason why we needed to make the change from the way we did things in the past to the way we're doing things today. And I'm not sure that we've seen that slide yet or that chart yet. And so my challenge out there is, I know you people are going to be showing some exciting stuff here at the conference. I'm excited about seeing it, but I think it's going to be interesting to see what's that chart that in 20 years, and hopefully sooner than that, but in 20 years we look back and we say, why didn't we, as a company, why didn't we make that jump earlier from the way we're doing things in the past to using quantum computing in more places, right? Because it really represents being able to get down into the nitty-gritty details of a problem and possibly doing optimization all the way up, not reducing order to do things. So so it's not an easy challenge. It's not an easy challenge because the bottom of the graphic here is about talking about the machines and the algorithms and the applications, right? There's always these existing camps of activity around the machines, the algorithms, and how those are applied to applications. And so whenever you kind of come up with a solution, you immediately get attacked. Like, well, we could do it this way, we could do it this way, we could do it this way. There's some corner case where this won't work. Yes, I agree. But we still need to think about how do we get this in there. And it's important, right? Because we struggle with, talking to our folks of saying, hey, look, you need to be thinking about this today because there's press coming out. There's improvements going on all the time in quantum computing. It's coming up a lot quicker than I think we even imagined, right? It's on this curve that we didn't think about. And so how do we do that? So that's what I'd like to kind of put out there to you. So kind of in closing, I'd like to thank you for your time. I'd like to thank Anna Rita Gianni, who's my colleague at GE. I'd like to thank the folks at GE and the folks at D-Wave who really made this exploration and this journey possible. And I hope you learned a little bit of how we bring customers into the quantum age, give them access to this machine, get them to use a quantum computer for the first time. We even give them coin to say, hey, that you actually ran a quantum computer. And hey, these are kind of the struggles that I think we see in the future. but I think it's a bright future, and it's ready for industrial scaling. So thank you very much, and have a great conference.